At this time, I'd like to introduce our presenter, Richard Roberts. Richard is Industry Affairs Manager for System Sensor and Honeywell Life Safety. Richard, take it away.
Thank you, David. I'd like to thank everyone for taking time from their busy schedules to attend today's informative presentation. Even though this is being presented by System Sensor, it is not a product sales pitch. Rather, it's an unbiased presentation that provides answers to several frequently asked questions and code-related requirements. The agenda for today will be to cover 3 important facts about carbon monoxide gas and CO detection. We'll review several key requirements in NFPA 720 relating to a systems-based approach to CO detection. Now, when I refer to a systems-based approach, I mean a system where CO detectors listed as complying with UL 2075 are connected to a control unit, not multiple station CO alarms listed as complying with UL 2034. And finally, we'll look at several states that have added requirements recently for the installation of CO detection. So let's get started. First, we'll talk about the alarm thresholds of CO alarms and detectors. That's because there's a lot of misinformation about the topic. Many people say by the time a CO detection device goes off, people are already poisoned, or that CO alarms are prone to false alarms because they are too sensitive. Actually, both statements are false. Let's take a look at the initial thresholds and why they were changed several years ago. This will help everyone to understand why some people are confused about the current requirements. So when first introduced in the late 1980s, CO detection devices were adequate, but they easily alarmed when exposed to long-term low levels of carbon monoxide. The one incident that gained considerable media attention, and is still talked about today, occurred in December of 1994 when the Chicago Fire Department responded to over 1,800 false alarms in a 24-hour period. This was due to a thermal weather inversion that trapped cold air under a layer of hot air, which prevented pollutants like automobile exhaust to escape into the atmosphere. Of course, CO is one of the main byproducts of found in car exhaust. The CO concentrations during this event were not dangerous, but they were high enough and long enough to cause CR alarms to activate. Needless to say, emergency first responders, UL, the industry were very concerned about the false alarm activations that occurred as a result of this incident and other activations that may have been caused by more short-term transient CO levels. Therefore, in 1998, UL and other stakeholders embarked on a project to update the alarm thresholds by adding several false alarm requirements to prevent these unwanted alarm activations. This important change requires no alarm but below 30 ppm until after 30 days, and no alarm at 70 ppm until after an hour. Now, the 30 ppm requirement is to protect against alarm activations due to long-term concentrations, such as from weather inversions. And the 70 ppm requirement is to protect against short-term concentrations that are caused, let's say, by a water heater or a furnace starting up. Now, as you can see, there are 2 product standards covering CO detection devices. The first standard is UL 2034, which covers single and multiple station alarms. These devices are self-contained and not intended to be connected to a control unit. The second standard is UL 2075, and it's the standard for detectors that are designed and listed to be connected to a control unit, such as a commercial fire alarm panel or a household combo fire security control unit. Even though there are 2 product standards, they both have the same alarm thresholds. So what are the current alarm thresholds? The first threshold is not actually an alarm set point. Rather, it's designed so the device will not alarm at 30 ppm until after 30 days. As mentioned in the previous slide, this requirement is to protect against alarm activations due to long-term low levels of CO. The first alarm threshold is designed so the CO device will activate at 70 ppm between 1 and 4 hours. The second alarm threshold is set so the CO device will activate at 150 ppm between 10 and 50 minutes. The last alarm threshold is designed so the device will activate at 400 ppm between 4 and 15 minutes. It's also important to point out the alarm thresholds that we just mentioned are intended to respond to the presence of carbon monoxide gas before a healthy adult loses their ability to react to dangers of carbon monoxide. Now let's switch gears and take a look at the various principles of CO detection. Both alarms and detectors monitor the amount of CO in the air over a specific time period, but they are really distinguished by their sensing technologies. There are three basic types of CO sensors used in today's marketplace. They are biomimetic, metal oxide semiconductor, and electrochemical sensors. Now, regardless of the sensing technology, all sensors used in single and multiple station alarms and system-connected detectors have a limited life. The lifespan ranges anywhere from 6 to 10 years, and that's depending on the sensing technology used and the manufacturer of the actual alarm or detector. The first technology we'll discuss is biomimetic. Now, biomimetic sensors really mimic how the human body reacts to carbon monoxide. Therefore, before we start explaining how these types of sensors operate, it's important to understand how CO reacts within the human body. Through the normal process of respiration, oxygen enters the lungs and is transported by hemoglobin that's found in the blood to various organs and tissues in the body, such as the heart and the brain. When CO is inhaled, it enters the bloodstream and attaches to hemoglobin, forming the carboxyhemoglobin molecule. Now, because CO is absorbed in the bloodstream over 200 times faster than oxygen, and it forms a stronger bond than oxygen, it reduces the ability of the blood to carry oxygen to the body's vital organs. So basically, people die from asphyxiation when they are exposed to high concentrations of CO gas over a long period of time. So getting back to the biomimetic sensor, they monitor the amount of infrared light that is passed through a disc of synthetic hemoglobin. The disc darkens in the presence of carbon monoxide. As CO concentrations increase, the light is absorbed, which then triggers an alarm. With metal oxide semiconductor technology, or it's more commonly referred to as MOS sensors, a tin dioxide semiconductor is heated by an electric current at regular intervals. When the tin dioxide reaches its operating temperature, it's capable of changing its resistance in the presence of carbon monoxide. Once the resistance reaches its predetermined threshold or thresholds, it triggers an alarm condition. Lastly, electrochemical sensors use an electrode and acid combination to promote a reaction between CO and oxygen in the air. This produces an electric current. When sufficient CO is present in the air and the current reaches beyond its specific predetermined thresholds, it will trigger an alarm signal. Now, as with any products or technologies, there are advantages and some drawbacks. And this is no different with each of the sensing technologies we just discussed. Biomimetic sensors require relatively low current draw to operate. However, these types of sensors have a long recovery time relative to the other two sensors, after an alarm activation. It could take as long as 15 or 20 minutes to recover from an alarm. MOS sensors have a long lifespan and recover quickly after an alarm activation. However, MOS sensors require a higher current draw than biomimetic or electrochemical sensors because it uses an electric current to heat the semiconductor. And lastly, electrochemical sensors have a relatively low current draw and they recover very quickly after an alarm activation. However, they may be susceptible to false alarms in the presence of very high concentrations of ammonia, and this is typically used in household products such as glass cleaners. Therefore, it's recommended to dampen a cloth with water to clean the housing of a CO alarm or detector instead of using a cloth that's saturated with ammonia. As mentioned a few slides ago, all CO sensors that are used in alarm and detectors have a limited life. Because of that, UL 2034 requires all alarms to indicate an audible end-of-life signal, and it has to be different from the alarm signal. UL 2075 requires all detectors to provide a means to send the sensor's end-of-life signal to the control unit. Now, for the 2012 edition of NFPA 720, that's the installation standard for carbon monoxide detection warning equipment, they added the following requirements to the standard. First, replace all alarms and detectors after the EOL, or the end-of-life signal, is activated. Secondly, replace combination smoke CO alarms after the end-of-life signal is activated, or 10 years from the date of manufacture, whichever comes first. Now let's switch gears and look at the placement requirements that are found in NFPA 720. And first we'll look at is for CO alarms and household CO detection systems. Section 9411 requires CO detection to be installed outside of each separate dwelling unit sleeping area in the immediate vicinity of bedrooms, on every occupiable level of a dwelling unit, including basements, but excluding attics and crawl spaces, and other locations where required by applicable laws, codes, or standards. Also, each alarm or detector shall be located on the wall or ceiling. Now, I'd like to point out that the IRC, that's the International Residential Code, and many state laws, they don't require CO devices to be installed on every level. Rather, many of them require CO detection to be installed in or near the bedroom. Therefore, it's always important to check with your local AHJ before designing or installing your CO alarms or detectors. Now, even though NFPA 720 requires a CO device to be installed outside of each bedroom, it's very important for the sound level to penetrate through closed doors into the bedroom to awaken people who are sleeping. The CO alarm or detector in the hallway may not be loud enough to wake someone who is sleeping because of a window air conditioner or a TV. This situation may require an additional device to be installed within the bedroom. Now, to make sure the sound level is high enough to wake people sleeping, Section 6441 of NFPA 720 requires the audible alarm signal to produce a sound level of at least 15 dB above the average ambient sound level, or 5 dB above the maximum sound level, or finally a sound level of at least 75 dB that's measured at the pillow. Now, looking at Section 55531, it requires CO detectors to be installed on the ceiling in the same room as a permanently installed fuel-burning appliance, centrally located on every occupiable level and in every HVAC zone of the building. Now, the reason CO detectors are required to be located on the ceiling above permanently installed fuel-burning appliances is because of the buoyancy of the heated combustion gases from the fuel burning appliance as compared to normal ambient temperatures. Now, a frequently asked question I get is, what is the weight of CO relative to the air? Some people say that CO devices should be installed near the floor because CO is heavier than air, while others say it is lighter than air, which means the CO device needs to be installed on the ceiling. Now, the simple fact is the molecular weight of CO is virtually identical to air. Specifically, the molecular weight of CO is 28 grams per mole, whereas the molecular weight of air is approximately 29 grams per mole. Therefore, that's the reason why in Chapter 9, a few slides ago that we talked about, CO alarms and detectors are permitted to be installed on the wall or the ceiling. Another frequently asked question is how CO disperses within a building. This question is best answered by a Fire Protection Research Foundation study that was concluded in 2007 by Hughes and Associates. This study was requested by the NFPA 720 Technical Committee to determine the placement requirements for these devices. The literature review concludes that CO disperses by two major mechanisms. First, by forced convection from mechanical ventilation systems. Secondly, from natural forces when mechanical ventilation systems are not present. Now, several examples of natural forces include solar heating through walls and windows, doors opening and closing, and occupant movement. The study also goes on to conclude that whenever a ventilation system is present and operating in most modern buildings, it will dominate the flow of CO in the building, and it will result in a very well-stirred environment within the ventilation zone. Okay, David, it looks like we're ready for our first poll question.
Very good, Richard. We do have a poll question ready, and we also have one question in queue, so we'll answer that during our poll question. If you could, in a moment or so, you'll see a poll question that'll pop up on your slide, on your screen there. If you could go ahead and answer it. And basically the question is, what are the factors that contribute to CO poisoning? Is it that length of time exposed, maybe the type of appliance, concentration of gases, or the season it occurs? If you could go ahead and answer that, we would appreciate if most or all of you could go ahead and vote on that poll question, and then we'll obviously publish the results here in a few moments. Richard, the question that comes in is there a specific definition of that immediate vicinity ruling? Does it have to be, say, a certain distance from the bedrooms? So how do you define immediate vicinity?
That is an excellent question and one that I frequently get. And as you can see, the requirement in the immediate vicinity is really very vague, and it's not very good code language. It really gets back to what I mentioned a few slides ago, and that is you really need to make sure that if you install a CO alarm or detector in the hallway outside of the bedroom or bedrooms, that with that bedroom door closed, that you're able to get 75 dB at the pillow to wake people up. So, you know, if you really have a large house, say you have 4 bedrooms on the second floor, and you got that common hallway between all the bedrooms, and especially in